Hello guys, welcome to the Ski Academia. If you're not subscribed to the channel, please do well to subscribe, hit the subscribe button. If you watch this video and of course you find it interesting and of course beneficial, please do well to like and also share. If you have any question whatsoever, also comment below. You have the comment box below. Drop your questions below and of course they'll be attended to. All right, so of course we'll be looking at sound waves today, and as a matter of fact, sound waves is a vital topic under the study of waves and optics. All right, so first of all, we need to know what sound is. So, sound can be defined as a compressional disturbance traveling through a given material medium and which enters the ear produces the sensation of hearing. So, when sound enters the ear, it produces hearing. Okay, so there are two keywords there. There are two keywords here. We have compressional, then we also have disturbance. All right, so it is known as a compressional disturbance which travels through a given, another word is material medium, through a given material medium. All right, so basically it leads to what we call hearing. So it brings about the phenomenon called hearing. All right. So sound waves can actually be classified into two. So the two classification of sound waves are: number one, we have what we call the shock waves. Shock waves. Number two, we have the elastic waves. So they are actually divided into two. We have the shock waves and we have the elastic wave. All right. So basically, one thing we need to understand is that when we look at the definition, if you remember, I said it is a compressional disturbance traveling. All right. So from the word traveling, we are made to understand that the word traveling there implies that, of course, there is motion, right? There is motion, right? Okay, so motion implies that, of course, traveling would have to do with a given speed. All right, and you know that speed is also known as velocity. So the velocity of sound in a solid medium is denoted as v. All right, and v has a formula. V is equals to the square root of e all over rho. All right, you know rho that looks like E, but not really E, which is used for resistivity at times. All right, so this is the formula for the velocity of sound in a solid medium. Now, E is denoted as Young modulus of the material. So this is the Young modulus. This is the Young modulus of this is the Young modulus of the material through which the sound travels. And of course, this is the density. This is the density of the material. All right. We can also call the material medium. All right. We can also call the material the medium, the means, the passage through which the sound travels. All right. So then that is for velocity in a solid. All right. Velocity of sound in a solid. Now, how about velocity of sound in a liquid or gas? Okay. So velocity of sound in a liquid or gas, V, is given as root B all over rho. All right. So this B here is known as adiabatic bulk modulus. Adiabatic bulk bulk modulus. All right. Adiabatic bulk modulus. All right. So it is more like the form of Young modulus of the material, but this time around it is actually when the of course the sound is traveling through a liquid or a gas. All right. But then when we look at this liquid, all right, when we look at this liquid, this is majorly for a liquid, all right, this is majorly for a liquid, all right, but most times too, fluids that have gases in it, okay, this can also work. But now we also have velocity of a pure gas, all right, velocity of a pure gas. So the velocity of a pure gas, okay, V is equals to the root of gamma P all over rho, gamma P all over rho, okay, and of course this P is known as the local pressure, okay, P is known as local pressure, then your rho is still density. But in this case now, you're not looking at the density of the material, you're looking at density of the gas. All right, the gas that is involved. Then of course the gamma, okay, gamma, which looks a little bit like Y, is actually known as the ratio of specific heat. Ratio of specific heat. That is what this is to denote. All right, ratio of specific heat. All right, so that is it basically. Now, one thing we need to understand that this local pressure P has its own formula as well. All right, so the formula for the local pressure P is equals to mRT all over V. All right, so M is known as the molecular weight, R is the is gas constant, okay, T is temperature, then of course V is volume. In this case, V does not denote velocity, denotes what? Volume. All right, and you know that molecular weight is more like molar mass, all right, or relative molar mass. R in this case is the rate constant, all right, the rate constant, which is 0.0821 atm dm cube per mole per Kelvin. All right. So this is the value for the rate constant. All right. Then of course you know that the temperature has to be expressed in Kelvin. All right. Temperature has to be expressed in Kelvin, and of course we have 273 Kelvin as the standard temperature. All right. So one thing we need to note is that generally the velocity of sound in any medium is directly proportional to the square root of the absolute temperature. All right, in any medium, the velocity is directly proportional to the square root, okay, to the square root of the absolute temperature. So we have something like this. All right, we have something like this. So there's also what we'll be looking at. All right, under velocity, we have different types of velocity. We have two types of velocity. In this case, when it comes to sound, we have the phase velocity, and we have also what we call the particle velocity. All right, so we have phase velocity and particle velocity. I'm going to be distinguishing both of them. All right, so let's define phase velocity quickly. Now, phase velocity is velocity in which the positions of the troughs, okay, positions or phases of the troughs or phases or mediums where the sound is actually traveling, okay, has a wave. All right, so we can also define it as the velocity with which positions of equal phases travel through a medium. All right, so positions of equal phases, and these phases are called crests and troughs. All right, so positions of equal phases, when there is actually a movement of these equal phases, all right, through a given medium, okay, through a given medium, it is called phase velocity. All right, phase velocity or wave velocity. So think of the two definitions I've given. All right, either you define it the first way or you define it the second way. Then we also have what we call particle velocity. Particle velocity is actually the simple harmonic velocity. That's another way of calling it simple SHV, simple harmonic velocity of a particle as it vibrates around a given position. All right, as it vibrates around a given position. So it's called simple harmonic velocity. All right, so basically these are the two types of velocity as regards sound waves. All right, so quickly now let's look at characteristics of sounds. Let's look at those things that will actually make us to understand that yes, okay, yes, sound is actually involved here, or more like factors that affect sound. All right, number one is pressure. All right. So pressure is actually a force acting in a medium over a given area. So that medium that the sound is traveling through, all right, that medium, the material that the sound is traveling through, the force that is acting on that medium, okay, over a given area, okay, where the sound is traveling, that force that is acting is known as pressure. All right. Then number two is power. Number two is power. Okay, so power is the energy transported per second by sound wave. All right. And remember, then for pressure, pressure is either measured in ATM, okay, it's measured in Newton per meter square, all right, or it's measured in Pascal. All right, Newton per meter square measured in Pascal. These are like three different units that can actually be used in measuring the pressure of a particular medium where the sound is traveling. All right, then power, of course, like I say, is the energy transported per second by sound wave. So that energy that is transported per second, the energy that more like pushes the sound wave through that medium is known as power. It's not the force. The force that it exerts on the medium, the force that exerts on the medium or that is exerted on the medium is pressure. All right, so power is measured in watts. This is the unit for power, or capital letter W. All right, then the number three, number three is what we call intensity. Intensity is denoted as I. All right, intensity. So intensity is denoted as I. What is intensity? Intensity is the rate of flow of energy per unit area. All right, so intensity is the rate of flow, okay, of energy. W, energy in this case, now we are looking at work done as the energy all over A. All right, so this is the cross sectional area. So the amount of energy, okay, that is required to move a particular sound wave through a given cross sectional area is what we call the intensity. Remember, power has to do with time. Power does not have to do with area, please. So don't mistake power for intensity. All right, don't mistake power for intensity. So this is W per A. All right, so of course your A has a formula. A is 4 pi r square. Remember that your pi is 3.142. Don't forget that. All right, it's like a constant. Okay, so intensity also have another formula. Okay, intensity has another formula. When you're giving pressure, intensity is directly proportional to the square of pressure. All right, so intensity is directly proportional to the square of pressure. So I've given you quite some formulas. So it means that I can also be able to be equal to rather P squared all over 2 rho V. Don't forget this rho. All right, that is standing for density. Okay, so it is actually P. This P, of course, is your pressure. Okay, don't forget that, not power. Okay, not power. So P here is pressure. Okay, so then you have 2 rho V. So intensity can actually be equals to P squared all over what? 2 rho V. Now, I want to also let you know that intensity is also directly proportional to power. All right, but it is directly proportional to the square of the pressure. All right, directly proportional to the square of the pressure. Now, so that's that for intensity. The next thing we'll be looking at is what we call timber. Not timber market. It's written like this, timber, not Timber. All right, so don't get it twisted. Don't mix them up. So what is timber? So timber is a measure of the quality of sound. Very simple, short. There is no other way of defining it. The measure of the quality. How is the quality of sound like? That is what is timber. All right. So that's just the short definition of it. Then another one is pitch. Another characteristic of sound is pitch. What is pitch? Pitch is actually the characteristic of sound that distinguishes a high note from a low note. All right, so it's that thing that can be able to differentiate a note. You know, sound produces notes. Okay, for singers, you know, where you're hitting a high note, that note is low. It's a lower note and all of that. The instrumentalist, you know that you play with notes. All right, you play with notes, and very important to understand that when you are trying to distinguish between a high note from a low note, what you are studying at that point in time is pitch. All right. So another characteristics of sound is what we call loudness. Loudness. So loudness is the relative strength of sound. Okay, relative strength of sound. So it is totally dependent on intensity. So I say it is the relative strength of sound. We can also call it the strength of sound. Okay, so sound has a higher strength, or you can say sound is stronger when it is louder. That's why we say relative strength of sound. All right. So of course, these are few characteristics of sound that we must take cognizance of, that we must know. All right, we must know. And we have many, okay? We have many. We also have there's one we also call resonance. Yes, resonance. Okay. So resonance is actually a phenomenon whereby an object is driven or forced at a frequency equal to its own natural frequency, and therefore resulting in maximum amplitude of vibration. That one is too much English. All right. Basically, what it is trying to say is that when an object, all right, is actually driven at a frequency that is the same with its own natural frequency, and it leads to vibration. That is what is called resonance, because every object has its own natural frequency. All right. So when you use another frequency that is almost the same, it's not the natural, but almost the same as the natural frequency, and of it leads to the formation of a maximum amplitude of vibration. Okay, that is what we call resonance. All right. And another one is what we call refraction. Another characteristic is refraction. All right. So refraction is the bending of sound waves. It's the opposite of reflection. Reflection is the bouncing of sound waves. But you cannot use reflection for sound in particular, because reflection mostly have to do with light. Reflection mostly have to do with light, but refraction is more applicable, is best applicable for sound, and as well for light, because of course refraction has to also do with the bending of light waves. All right, so it's very important. So these are a few. All right, so now basically, I want to be defining a phenomenon, all right, a phenomenon for us, which is called the Doppler effect. It's called Doppler, Doppler, Doppler's effect. All right, so what is Doppler's effect? Very simple. Doppler's effect is actually the apparent change. Apparent means apparent. The word apparent means obvious. All right, apparent means obvious. So it is the apparent change in the frequency or pitch of sound due to relative motion between the sound source and an observer. Okay, so when you actually have an apparent change, an obvious change, you experience an obvious change in the frequency or pitch of sound, which is of also due to the relative motion between the source, okay, and the observer. The observer is called the listener. Okay, so when there is a clear change in sound, okay, you are listening to the sound, then the sound changes. All right, the sound changes. Obvious change is not the one that you didn't really notice. So it's an obvious change between the source and the observer, the listener. Okay, that obvious change is what we call Doppler effect. All right, Doppler effect. So basically, it's very important to note that. Very important to note that. So we'll be looking at a couple of examples, that will help us to actually understand sound waves better. All right, we're looking at examples, and in the process of looking at examples, I'll also be giving you some formulas, all right, that applies to the examples that we are going to be treating. All right. Now, the first example we're looking at is this. You can put down as I'm dictating: at a temperature of 20 degrees Celsius, the velocity of sound in a medium was 344 meters per second. What is the velocity at a temperature of 45 degrees Celsius? Okay, this is simple. So we are told that at a temperature of 20 degrees Celsius. All right, so it means that we can say T1 is 20 degrees Celsius. All right, then the velocity at that temperature, which is V1 was 344 meters per second. All right, so then of course our T2, we are told that the T2 was 45 degrees Celsius. All right, so we are looking for the second velocity unknown. All right, so you need to understand that of course we have to convert this to Kelvin, and converting it to Kelvin implies that we will say 20 plus 273. All right, that will give us 293 Kelvin. Convert this as well to Kelvin. So we say 45 plus 273. All right, plus 273 to give us 318 Kelvin. because you know that the standard unit for temperature that we must make use of is the one in Kelvin, not degrees Celsius. All right, so basically, I'll be giving you the formula that we'll be using. All right, I'll give you the formula that we'll be using. So, um, take down. So, the formula, one thing we need to understand is that, remember, I told you that V is directly proportional to root T. All right, so it means that we can say V1 all over root T1 is equals to V2 all over root T2. Okay, and we are looking for V2 in this question. So V2 will be equals to V1 root T2 over T1. All right, making V2 solid to a formula. So solving that quickly, it means that, remember, our V, we are looking for V2. So our V1 was 344. All right, times root our T2 was 318 all over 293. All right, so if you plug that in our calculator, straight up, we'll have now 344, okay, times square root of 318 divided by 293. So this will give us 358. This will give us 358.38. All right, 358.38 meters per second. Okay, so this is our V2. These are V2. All right. So this is just one out of many examples that we are going to be solving. All right. So this is 358.38 meters per second. This is the second velocity. These are V2. And please mind you, this V we are using is not capital letter V, it's small letter v. Anytime you see small letter v, it indicates velocity. Capital letter V mostly indicates volume. All right. All right. So now let us look at another example. Please take down. Now a source produces 100 watts of seconds. All right. A source produces 100 watts of sound, rather. Sorry, 100 watts of sound. Now full stop. If the energy spreads out spherically, determine the intensity of the sound at a distance of 100 meters. So we will use arrow to denote distance. So arrow is given to us as 100 meters. All right, so we're looking for intensity. Intensity I is equal to, remember I told you that it's power all over area, and area is 4 pi r squared. All right, 4 pi r squared. Now one thing you need to understand is that, okay, one thing you need to understand is that power can be used together with work done. It can be used together with energy. All right, if you're giving power, okay, because I gave you W all over A, remember, right? But if you're giving power, you can actually use it. You can actually use it to represent W. They can work in pari passu. They can work hand in hand. So power over area is also, of course, intensity. So now P all over A. So let us solve it quickly. So in this question, we don't have area, all right, but we can look for area. So I can see that I is equal to 100 watts divided by, remember I told you 4 pi r squared, okay, 4 pi r squared. This is 100 divided by 4 times 3.142 times, your r in this question is 100. All right, 100 all squared. All right, so let's do that quickly in our calculator. So we have 100 divided by 4 times 3.142 times 100 all squared. All right, 100 all squared. So solving that now will give us 7.956. Okay, so we have 7.9 on approximately 7.9. So it means our I equals to 7.96 times 10 raised to power minus 4 watts per meter square. Remember that area is in meter square and power is in watts, so it's important to express it this way. 7.96 times 10 raised to power minus 4 watts per meter square. That is our answer. Okay, so let's look at example 3. Let's look at example 3. Okay, let's look at example 3. So I told example, when the sound pressure in the air exceeds 30 Newton per meter squared at 1000 hertz. Okay, hertz of course is the unit for frequency. Okay, now the human ear feels pain. All right, the human ear feels pain. Now find the intensity, at this pressure. That's the first, the intensity at this pressure. Then B, the characteristic impedance, all right, of the medium of the ear, all right, of the ear. So basically, when we say characteristics impedance, now we are going to be looking at these two questions and we'll be solving them with the given parameters. All right, so I've listed the two parts of the question. So now let us look at the intensity at this pressure first. Let's look for the intensity at this pressure. All right, let's look for the intensity at this pressure. Now, basically, I will be equals to P squared all over 2 rho V. Remember this formula I gave you. This V is small, remember. Okay, so this would basically be 30 all square divided by 2 times. Now remember, okay, that basically from the question, the question was a little bit incomplete. All right, so in bracket you put density of air to be 1.21 kilogram per meter cube, velocity of sound in air 3.43 meter per second. All right, so then it will be given to you. If you have a question like this, they will give you the density of air. All right, so this will now be 2 times 1.21. Remember, I told you that the density of air is 1.21 kilogram per meter cube. So 1.21, then times your V, which is 3.43. This V here I told you is the velocity of sound in air. These are constants. All right, these are constants. So let us solve this quickly with our calculator. So we have 30 all squared. Come down 2 times 1.21 times 3.43. So this will give us 108, okay, 108.43, approximately 108.43. Okay, so it will give us 108.43 watts per meter squared. All right, so this is the unit. Remember, watts per meter square. So basically, that's for the intensity at the pressure, okay, at the pressure that has been given. You are given a pressure. This is not power here. This is representing pressure. So don't mix them up. Look at what is in the question because they will state is it power or is it pressure. All right. So that is it basically. All right. So now let us look at the second one, the characteristic impedance. Now, characteristic impedance or impedance is denoted as Z. Okay, so Z is equal to the density times the velocity. It's the product of density and velocity. All right, very simple. So this is 1.21 times 3.43. All right, okay. So 1.21 times 3.43. All right, so this will give us 4.15. So